Hi. For the final project of CIS 660, Songhe and I were doing a Maya plugin called Midas. As all of you have already known, Maya is good at modeling. However, turning a mesh into a solid object as it is in real world is not a trivial task. Also in industry, there's a production need for turning geometry meshes into solid objects. Therefore, we developed this plugin for Maya, helping those animators to finish their work easier and better. As you may notice later, our tool consists of two parts. One is called shape matching, and the other is called shape matching group with oriented particles, both of which are capable to turn meshes into solid objects with only a few simple operations. As theoretical foundation, we refer to three of Matthias Müller's paper. For the first one, we are implementing based on meshless deformation based on shape matching with paper. And for the second one, we took advantage of all three papers. So technically, the first two is a subset of the second one. For implementation, we split our work in a good manner. Songhe is in charge of the Maya integration, and I was in charge of designing the structure and solver node. Both Mail and C++ are used for Maya integration, and the solver part is purely C++. We built everything from scratch, and the only third-party library used is the SBN linear algebra library from online. Now let's turn to see how the plugin works and what the user needs to know. Here's a video showing the basic workflow of our main tool. The first thing we need to do is to spray particles. Here I'm showing the UV map method. The density that I've tuned determines the number of the particles that is to be sprayed. After that, we create the edges to form a skeleton for the object. Both automatic and manual tools are used here. After the skeleton is built, we raise the particles radius to bound more vertices. By clicking Create Solver Node button, the particles will be initialized to bound the containing vertices in a better way. And one last thing to do is to change the stiffness of oriented particles, deciding how rigid you want the object to be. 0 stands for totally soft and 1 means rigid body. Actually, we could change the stiffness during the simulation and the object would respond to that simultaneously. You can see the result here. If we change the stiffness of the particle, the object will respond to that simultaneously. Here's another video showing the basic shape matching tool. Compared to the previous one, this tool requires only one click from the user. Similarly, users are allowed to change the stiffness according to their needs. You can see the result here. If we change the stiffness like this, the result would be changing because we are using 0 stiffness, and now we change it back to 1. It's a rigid body again. Also, users are allowed to spray particles based on their own interests. However, particles are actually representing the object, so the better you spray the particle, the better result you will get. Here I'm using 8 particles to represent the torus, and the result, as you can see, is pretty satisfying. Now I will turn back to my slides and focusing on the future work and the performance analysis. Between the two tools, I prefer the first one because it requires less operation, it's simpler, and it's also more efficient. Because the second method relies on heavy iteration to find a balance between the multiple geometry constraints. For the future work, we'll be working on improving the performance of this plugin and also try to add in more features like the user interface.